So good morning, Patty. Welcome to Turbulence. We'll continue the lectures. We are on chapter 6, discussing free shear flows, specifically jets. And we worked up a lot of empirical equations and showed you what has been found to describe dynamics of jets. But we haven't yet delve down into the transport equations. That's the main purpose of today. So let's pick up where we left last time. Reynolds stresses, we said they can be defined for any type of flow, not just wall flows, but in addition, free shear flows such as jets are. The stress tensor has 9 components where you pair different components of fluctuations. For example, U with itself, U squared, V with itself, V squared, W squared. And you have the cross correlations, UV and VU. And we told you all of the cross correlations involving W, such as UW and VW, must be 0 because the jet is axisymmetric. There's no reason why there should be a cross correlation in the circumferential direction. Okay, so we talked about that. Then we moved on to consider the root mean square of axial velocity on the center line, defined as U naught prime. So this symbol shows you, the 0 shows you the quantity of interest on the axis of symmetry of the jet, and we take the square root of the U variance to get the standard deviation, if you will. So this prime here shows you're looking at the standard deviation, not the variance. So now this is new material on this page. We wish to characterize how this standard deviation or fluctuation will vary as a function of x, or equivalently in terms of the non-dimensional quantities, how the ratio of this fluctuation with respect to the mean axial velocity varies with non-dimensional distance downstream of the jet. It has been observed that after the development region of the jet, i.e. after the virtual origin, both of these quantities, fluctuation of the axial velocity and the mean axial velocity of the central axis, decay as the inverse of x. So this has been observed. In a similar way to mean velocities, it has been found that the Reynolds stresses become self-similar as well. So the profiles of the Reynolds stresses now plotted against non-dimensional radial distance. If you remember, the R1/2 was the half width of the jet. It's the radial distance at which axial velocity drops by 1/2. Or the similarity variable, R divided by x minus x naught, collapse for all x beyond the development region on the same curve. So, as discussed, the structure of the jet is self-similar. It looks like a triangle, right? So you can fit a lot of similarity variables to it and find correlations. Let me underline a few more sentences. The Reynolds stress exhibits significant anisotropy. So, if you remember, isotropy or anisotropy had to do with rotation of the coordinate system. And we said you might, for a given coordinate system, you might measure certain fluctuations or components of Reynolds stress. This could be U, for example, U squared, V squared, W squared, or any combinations. We told you if you rotate the coordinate system, you might measure different components of the Reynolds stress. In the same flow, if you rotate the coordinate system, you measure different components. If that is so, you have an isotropic flow. And here I'm saying that jets are extremely anisotropic. So the fluctuations vary quite significantly given the direction. The relative magnitude of the shear stress compared to the normal stresses can be quantified using this relationship. Basically, the cross correlation of axial and radial velocity divided by kinetic energy, for most jets it's about 0.27. I should remind you what kinetic energy was. So this is just a reminder. K is equal to 1/2 U squared plus V squared plus W squared. So if you add all of them up, you get the kinetic energy of the jet. Here I'm saying the cross correlation, or the shear component of the Reynolds stress divided by this kinetic energy for most jets is about 0.27, almost everywhere in the self-similar region. Okay? Doesn't matter where you measure. The velocity fluctuations of u and v are also found to be correlated with a correlation coefficient of 0.4. So here I would like to again define what this symbol means. This is rho uv. This must not be confused with density or other things that we have defined for you, but this simply means correlation coefficient between u and v. And correlation coefficient can be anywhere from -1 to 1. If it's 0, there is no correlation between two random events of interest. If it's -1, it means they're exactly anti-correlated. If it's +1, that means they're exactly positively correlated. So if this coefficient is 0.4, that means they are almost correlated. Which means when you get a fluctuation in the u direction, most likely you will get a fluctuation in the v, radial direction, right? So sort of both go up, they're positively correlated, or they both go down. So these two components of fluctuations are positively correlated. And numerous functions have been fitted to describe round jets. Most of them combine a polynomial times exponential fit to the quantity of interest. If you remember, we said the similarity variable for a jet can be defined as eta, defined as radial distance divided by the horizontal distance. And we say in the self-similar region where this quantity is less than 0.2, you can fit a lot of the turbulence statistics using this function in the radial direction. Obviously, there is r here. And if r varies, eta varies. Likewise, x varies too, eta varies. So the similarity variable combines r and x, or radial and axial distance. And for any quantity of interest, these constants would change. You might be looking at mean velocity, you might be looking at variances, you might be looking at covariances. So this can be used. And I can show you a table, but let me underline these sentences because it's important. The multiplication of the polynomial and exponential functions provides an excellent fit over a range in which data was taken in previous studies. So only in this range, or basically in the self-similar range, not too far away from the jet, either axial or radial direction, but by and large in the self-similar region. So you must be careful not to use this fit everywhere. Okay? Always make sure you check for this. Now, I'll show you the table. So here, P could be any variable of interest. And here I'm showing you some of the examples. If you're interested in mean flow in the axial direction divided by mean flow on the central axis, you normalize the axial direction. These are the constants you should use for that fit. So you put these constants in that fit and you calculate the value of eta and you calculate mean flow anywhere. Doesn't have to be on the central axis, could be on the side in the radial direction. Variances, again, you can put the constants of interest and calculate your variance. So is covariance, also has its own fitted constants. Dissipation rate too can be fitted. And even though I haven't defined this dissipation rate for you yet, but I will in the next chapter. It's a very important quantity, if you will. It's another statistics, very important in understanding turbulent flows. So again, that can be fitted. So very practical. Questions? So far so good. Now that, as promised, I will show you the mean continuity and momentum equations for a jet. Mean continuity and momentum equations. So now we wish to derive the mean continuity and momentum equations for a two-dimensional jet. So be careful, we're going to make the case simple. As if this jet exists in a plane. It's not a three-dimensional jet, it just exists on a plane. The jet axis is in the x direction, and the lateral axis is y. So essentially I'm saying r is y. So the radial distance, you think of it as y. So that means far away from the jet in the lateral direction, y should approach infinity. And in those regions, the fluid is quiescent at some background pressure. So if you like, you can put a picture to it. So here's your jet. Here's your jet, x, y. So here's your jet. So your jet is going from left to right. Okay, that's your jet. That's U naught. And outside you have background quiescent pressure P naught. I mean, this could be P naught all around the jet where the jet does not have an influence. So all around this jet you have background pressure P naught. The continuity equation requires that partial u partial x plus partial v partial y be 0. So this must hold. Because your jet is constant property flow, it's not compressible flow and whatnot. So this will hold. Now I will discuss the momentum equation. In both the x and y directions. And I will put in significant terms in curly brackets when I show you the equations. You'll see it coming up briefly. One thing I would like to do before I show you the equation is to tell you the approximations I'm going to use. So here's your jet, it's coming into the quiescent background. So that's your jet. This is the x-axis, that's the y or r-axis, the lateral radial direction. And the jet comes in and then develops. So the momentum equations that I will write will give me the velocity profile anywhere. So that's the purpose of the momentum equation. So I would like to write it for both x and y directions. But I'm going to make some assumptions. For computation of Reynolds stresses, I'm going to assume there is very little variation in the x direction. However, variations in the y directions are not necessarily zero. So what I mean is, most Reynolds stress components don't vary significantly along the jet. Let's say if the jet is going this way, that's the x direction. The u squared, say fluctuations of u, don't change as a function of x. If I measure it here, it's the same as here, it's the same as here. Fluctuations v don't vary appreciably along the jet, or uv or uw. But in the radial directions, they start changing significantly. So u here is different from u here, is different from u here. Okay, so I'm only writing these for the components of Reynolds stresses, not mean quantities. Obviously, mean velocity varies. The jet slows down and whatnot. So here are the equations. So let me show you the equation for the u component of velocity. So the transport equation is being written for u. For u adding as well as u component of velocity. So that's why I have u appearing here. That's the variable of interest, right? U, that's all, and also the u here and the u there. Also, u is in the x direction. That's why the normal body force is showing up with a partial x, right? So these all tell you I'm writing the x component of momentum. All the u's and x's you see assure you of that. I promised you I would label the terms, so that's what I would do. So here you see the advection term in the transport equation. That's where these u and v come. You see the surface forces. These are basically viscous forces applying to the faces of the control volume. The shear stress force, that was a component of the Reynolds stress tensor, right? It's there. There's another component of the Reynolds stress term here. Of course, Reynolds stress contains both shear and normal forces. And finally, I have the normal and body forces. So there's no body force here because I'm ignoring gravity, but I could have gravity here too. So these are all the terms. So I put curly bracket along some of the terms because I would like to ignore them. First of all, I just told you that components of Reynolds stress don't vary much in the x direction. So as a result, I'm going to ignore this normal stress term because it's the component of Reynolds stress, partial x. I would like to ignore that, so I put curly bracket. Also, I would ignore this term, which is a second derivative of mean velocity, based on the assumption that there may be a derivative of mean velocity in the x direction, but there's no second derivative, so that the curve doesn't exhibit any curvature, right? Second derivative gives you curvature. So I assume that is not there. So I have some terms left. For the v component of the momentum, I'll do the same. First of all, I should convince you this is V component of momentum. You see momentum in the y direction. V appears here. V, 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 and then you get y here, right? So that's the V component of momentum. There's the advection term. There's the surface force, shear stress, normal and y force. And I'm going to ignore more terms here. So I'm ignoring the Reynolds stress derivative in the x direction, so I ignore that one. I'm ignoring all second derivatives based on the fact that mean profiles of V component or U component of momentum don't exhibit any curvature, so I ignore those. I also ignore the advection terms based on the fact that, first of all, V is much smaller than U. Remember, we said V is in the order of 2 or 3% of U, so I can ignore that. So I can ignore derivatives of V with respect to x also. So the V component of momentum actually boils down to a much simpler equation. I actually only have 2 terms left. So this plus that was equal to 0. Okay? Now as exercise, you might at home try to derive this for a jet. I mean, you should be, by this time, you should be able to do this, to write the general form of the Navier-Stokes equation for momentum and reduce it down to here. You should be able to do that. Maybe a nice exam problem. I will reinforce the assumptions one more time here in the text. I can underline so the material will settle in. The rationale for the neglected terms in curly bracket are as follows. All terms containing a partial derivative of V are neglected, since mean velocity in the lateral direction was really small. Remember the water hose example? Like jets mainly go in the axial direction. They don't immediately expand to the radial direction. If you've got a water stream going out, it just keeps going forward. It only very gradually expands. So the radial component of velocity is very small, maybe less than 2 or 3% of the axial one. Also, all partial derivatives of the components of Reynolds stress involving both normal and shear stresses with respect to the x should be neglected because these derivatives are insignificant with respect to the derivatives in the y direction. That's what I said here, okay? I'm going to ignore the x derivatives of Reynolds stress components. Finally, I also ignore the second derivatives with respect to x or y because there's very little curvature. Well, just y, just x, not y. So basically, second derivatives, that means I assume second derivatives to be 0 too. Which I had some instances of here. So I had one here, second derivative with respect to x, I assume 0. Another one here, I assume that being 0 too. A lot of assumptions. It appears there is some arbitrariness in what we do. I mean, obviously, as a fresh graduate student, you may not see how you might reduce it, but with experience and the level of approximation you want to make in your problem, you have the authority to make some assumptions, and if you know enough about the physics of the problem, you can assume some 0 terms in these transport equations. So with all of these, the mean lateral momentum equation simplifies to the following. I started with the V component because it was more simple, there was very few terms left. So So partial derivative of pressure with respect to y is plus partial derivative of the Reynolds stress normal component v is equal to 0. You can integrate this from any arbitrary point to infinity and arrive at another expression given here. We did this type of integration in chapter on wall flows. You can try that at home. You get this. And it shouldn't be too difficult because this is just the ordinary differential equation. So the derivative of something is equal to 0, so that something should be a constant. Right? It's as simple as that sounds. And the constant is background pressure. You know. And now we apply the same trick, and now we differentiate this with respect to x. We did the same thing in wall flows. So to be able to give the axial pressure gradient as a function of the far field pressure, and we know. And it's very interesting if you take derivative now, well, P naught was a constant. That was the quiescent pressure in the quiescent fluid. All around the fluid, it's the same number. It's not going to vary. So that term must be 0. Also, remember what I said. Components of Reynolds stress do not vary in the x direction. So both terms are 0. So it looks like pressure itself must not vary in the x direction. That also must be. The gradient must be 0. It's a very profound result. Which means this. It means that, remember, we said here's the jet. So the jet goes into a background. The pressure all around in the quiescent background is P naught. I just convinced you pressure in the jet should not change in the x direction. That means anywhere in the jet you look, pressure is going to remain the same. For example, if the pressure is P here in this point, it's P here again, like let's say P1. P1, P1, P1. If pressure is here P2, in the axial direction is P2 and so on. If it's P3 here, it's going to remain as P3. Pressure is not changing in the axial direction. So basically, partial P, partial x is almost 0. Goes without saying that this was the x direction. That was y or r. Very profound result. This is exactly opposite to wall flows. In wall flows, it was the pressure gradient that was pushing the fluid forward and the friction was stopping it. So in wall flows, there was a pressure gradient in the x direction. Here, there's no pressure gradient. It's the momentum of the jet that's pushing it forward. And jet will eventually stop because it can't keep going indefinitely. It will get stopped by the friction of the background fluid at some point. And the water was example, if you make a water jet, it doesn't go indefinitely, it eventually stops going. Which is valid in quiescent background. Just underline a few words here, which is valid in the quiescent background because P naught is uniform, and then we already assume partial derivatives of Reynolds stress components in the x direction are negligible. That was that assumption. These developments result in a much shorter version of the mean momentum in the axial direction. So now I want to go and rewrite the other transport equation for momentum in the x direction, basically u. This comes from the previous page, but now I know the pressure had no gradient, so I just get rid of that term. So now that's all I have. U, and a couple of derivatives there. So this is the momentum equation. In fact, if you solve this equation, you will get the jet flow. You will get a solution for the flow. You get all the details of the flow wherever you're interested to calculate. This is not something you can calculate by hand. You must write a simple computer program, maybe Python or MATLAB to do it. Okay. And that would close the chapter on jet flows. Before I do exercises, maybe recap. So what we did in the previous chapter, we introduced wall flows to you and simplified Navier-Stokes equations and came up with some easy versions of them which you can solve. In the free shear flows, naming round jets, we did the same. We did develop some empirical equations to show you how round jets behave, and then again we simplified the Navier-Stokes equations and showed you how they look like. So we followed the same approach, methodology. And these are the only two classes of flows I would treat in this way. As I said, there are books, volumes and volumes of books on all types of flows. Wall flows, free shear flows, shock flows, buoyant flows, compressible flows, supersonic flows. But the purpose here in this fundamental course is not to discover all, but just show you the essence. Any questions before I do an exercise? That's good. Any questions from online? Leave a comment, please. Let us do the exercise. So let me see which one I want to do. I want to do exercise number 1 for you. A round jet is produced by a nozzle with some given diameter 1 centimeter. The jet exit velocity is 1 meters per second. Making the necessary assumptions at some position half a meter away from the jet, show that the jet's mean axial velocity and the jet's half-width distance are given by these numbers. So mean axial velocity is at half a meter is 0.13 meters per second. And half distance at that location is 0.047 meters, 4.7 centimeters. So let's do that. Example 1. Jet diameter is 0.01 meter. Jet exit velocity is 1 meters per second. Axial distance is 0.5 meters. So that's the distance of interest. I want to analyze my jet. Let's draw a schematic. So here's my jet. Diameter d. As we said, this jet is not going to exhibit self-similarity immediately. It will exhibit that after some initial distance. Remember, that's the onset of self-similar behavior. And we said that point is called the virtual origin, x naught. So after x naught, jet exhibits self-similarity. It looks like a triangle. So here's my central axis of the jet. I'm interested in a location x equal to 0.5 meter. So that's the point of interest. And the jet is going to exhibit some profile. At the center, it's going to have mean velocity u naught at x equal to 0.5 meters. And here it's going to exhibit half of u naught x equal to 0.5 meter. And this radial distance, where axial velocity is 1/2 of the central axis, is known as r1/2. So r1/2, if you like, is also a function of axial position. We want to know what r1/2 is, and we want to know what u naught is. We know that u naught satisfies this equation. Also, we know in the self-similar region, x naught over d is in the order of 4. So in fact, x naught is equal to 4d. Even though the problem doesn't give you the value of x naught or the virtual origin, you can calculate it knowing this relationship from the chapter. We know that d is 5.9, that's the constant that was found by Hussein et al. And it's a constant that was fitted to the self-similar behavior equation for it. And then I can make the substitution. Uj is 1 meters per second. B is 5.9. D is 0.01 meter. Denominator, I have 0.5 meter minus 4 times d. 4 times 0.01 meter. So the velocity at that location is going to be 0.128 meters per second. So what did I calculate? I just calculated u naught of 0.5. I substitute x equal to 0.5 there. I'm going to find half width using the relationship for a spreading. If you remember, S was a spreading. And we told you for most jets, spreading rate, S is about 0.1. And specifically, it's 0.102. So spreading at, I put spreading here, 0.102. Location of interest was 0.5 meter minus 4 times 0.01 meter. And I calculate the half width to be 0.0469 meter. Remember, S was a spreading of the jet. A spreading around jet. This was a very empirical type problem. I didn't ask you to massage the Navier-Stokes equations. Very short problem, back of the envelope calculation. Although in the computer world you might develop very rigorous models of a jet and develop numerical methods to solve its motions. Sounds good? This next chapter is my favorite. I am serious. Chapter 7 is scales of turbulent motion. It's a very deep, fundamental chapter, and most of the breakthroughs in turbulence research and the knowledge that we have and the great things we do comes from this chapter. So this is the type of chapter that the physicists would love, because they see what went in the mind of the great giants and figures who developed the theory and what enabled them to come up with great solutions to this problem. Why do I call it scales? Because remember, fluctuations in flow come and go, and they exhibit different scales. If you think of fluctuations as eddies have a length scale. They can be large and they can be big. Eddies could have a velocity scale. Fluctuations could have high velocity, low velocity. Eddies could have different time scales. They can appear and disappear at with different time constants. A fluctuation may last for 1 second, may last for 10 seconds, may last for a fraction of a millisecond, right? So it's all about the scales. The study of the scales of turbulent motion revolves around the understanding of various time, length, and velocity scales, at which turbulent motion forms and progresses. So that's what I just said. The pioneering work in understanding the scales of turbulent flow was done by Louis Fried Richardson. He was a British scientist who coined the word energy cascade, and he came up with hypotheses. Richardson was a very interesting person, like a pacifist, lived during the Great Wars, the First and Second World War. In fact, he was very interested in weather forecasting, weather prediction. So in some circles, he is known as the grandfather of weather forecasting. He thought it would never be possible to do it fast enough to be useful to humankind, because at the time, computers were not around, and especially fast computers were not accessible to the ordinary meteorologists. But within a couple of decades, it all became possible. So we all owe it to him, the idea of simulating weather systems and coming up with forecasts and predictions. And Richardson basically put the hypothesis out in word. According to his hypothesis, turbulent kinetic energy is produced and enters a turbulent flow at the largest length scales of motion, which means that first very big and huge eddies form. This energy is then transferred by invisible processes to smaller and smaller scales, until at the small scales the energy is dissipated by viscous action. I told you this in chapter 1, introduction, and in fact we also looked at his poems, which says big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. So the whirl is an eddy, if you like. Whirl is an eddy. He understood this, but he could not formulate it mathematically. Okay, he was a very good mathematician, but not good enough to formulate this mathematics. So then the next giant appeared, Andrei Nikolaevich Kolmogorov, and he was a Russian mathematician who finally came up with a mathematical theory, and he actually quantified the energy cascade hypothesis using mathematical formulation, and he came up with his own hypotheses to be able to do this wonderful job of formulating the energy cascade process. This is a big deal. I mean, it's by these hypotheses and formulations that finally we are able to solve real engineering and science problems. We all owe it to them. Let us now do the details. The energy cascade and Kolmogorov hypotheses. Consider the turbulent flow with characteristic velocity scale u and characteristic length scale L and a Reynolds number. And suppose that this Reynolds number is very high. And we should have no trouble understanding the concept of scale, right? Any Reynolds number calculation requires size and velocity. Take flow in the pipe. Okay. What is the size of the pipe? Characteristic length scale is the diameter of the pipe. What is the velocity? Is the average velocity of flow in that pipe, or water channel. Okay, so, and of course the fluid with some kinematic viscosity, you can calculate the Reynolds number. It must be very high for the hypothesis to work. Russell Richardson said that eddies that form have a size, L, have a characteristic velocity u as a function of that size, and a time scale tau also as a function of that size, and subsequently velocity. So this L, this fancy L, shows you the characteristic size for an eddy. If this fluctuation is big, L is large. If this fluctuation is small, L is small. U is the velocity of the fluctuation. Remember, not the velocity of the mean flow. The background fluid could move fast or slow. I don't care about that. I care about the fluctuation, right? Let's say if there was a fluctuation like that was moving very slowly, this U would be small. But the fluctuation, if it was fast, then U would be large. So it's the velocity of the fluctuation. And time is how long it takes for the fluctuation to happen. I mean, it could happen slowly, it could happen very fast. And this should not surprise you because, well, for any motion, the most simple formulation of motion is this. Velocity is defined as distance over time. Velocity defined as distance over time. You can do it here. Velocity is defined as distance over time. So time is distance over velocity, right? Velocity, time, distance. That should not surprise you why. Time scale of the eddy is equal to its size divided by velocity, because it must. So we know that these eddies have some size. Now I'm going to look at some specific types of eddies, only the largest ones. The largest eddies that are formed in turbulent flow are designated with subscript 0. So when I say L naught, I mean the size of the largest eddies. And I'm also saying that this L naught is comparable to the length scale of the flow. Let's say if you had a pipe, the length scale of the pipe is the diameter. If an eddy formed in that pipe, L naught is not much smaller than the size of the pipe itself. If the diameter is, let's say, 1 meter, the largest fluctuation that can happen is by and large 1 meter, right? Maybe it's 0.8 meters, or maybe 1.2 meters, but it's close. It's not 1 millimeter. So L naught and the scale of the flow, length scale of the flow, are on the same order. If you like, L naught is in the order of the length scale of the flow. Likewise, the velocity associated with these eddies are comparable to the length scale of the flow. So in other words, U naught is also in the order of the velocity scale of the flow, which means that if I had this pipe, fluid was going at 1 meter per second, the velocity of the fluctuation is the largest fluctuation, by and large, could be the same velocity as the flow itself. If you want, so let me just put a small picture here for you to visualize this. So that was the eddy, and I told you eddy is a spinning structure of the fluid. So let's think of it as a circle. So this larger eddy has some size, right? If the size of that circle, let's say diameter, is L naught, it's happening by spinning by some sort of velocity U naught, it's the largest, and it's going to last for time scale tau naught. Obviously, the energy cascade requires this to break down to smaller size, say L, and some velocity U and some time, and it's going to keep breaking down and so on. So here I'm talking about the largest ones. These velocities of the largest eddies are in the order of velocity fluctuations and related to the root mean square of the turbulence kinetic energy. Remember K, I just told you a couple of minutes ago, during the beginning of the lecture, K is the turbulence kinetic energy. Well, this by definition is the sum of the three variances of Reynolds stress, U squared, V squared, W squared, right? So if think of it, if I divide by 3 times 2, take the square root, I should get by and large the fluctuation scale. So this should not surprise you. This is just by definition. It is possible to associate Reynolds number to these eddies. So now I'm saying not only I have a Reynolds number for the flow, but I can also have a Reynolds number for the eddy, for which the velocity and length scale change here, right? It's U naught and L naught. But I already told you these are close to the scales of the flow. So this Reynolds number for the largest eddy should be also close or comparable to the Reynolds number of the flow itself. If you like, Reynolds number of the largest eddies are comparable to the Reynolds number of the flow as well. I should also say at this scale the effect of viscosity is negligible, because really it's the inertia that dominates turbulence. I mean, turbulence happens because of high inertial forces. Viscosity should be not that important in this range. If it was important anyway, the flow would be laminar. Right? Think about it. Reynolds number. For you to get a high Reynolds number, viscosity should be small. Right? So really, viscosity is not a game changer at the largest scales of the turbulent flow. It's in fact it's the lack of it that results in these fluctuations and eddies. And then the energy hypothesis says, yeah, then these large eddies continue to break down to smaller scales. And at each scale you have a Reynolds number associated with that scale. And the Reynolds number can be calculated having length scale of the stage of interest and velocity. Of course, the viscosity is the same, so this also has a Reynolds number at this scale along the energy cascade. But this Reynolds number of the subsequent breakups gets smaller and smaller. At some point, the Reynolds number becomes very small, in which case, at that scale, then viscosity kicks in. So if you like, if you go all the way down, at the end of this, Reynolds number should approach a small number, which would say that there's no longer the inertial effects are important, and at that point, viscosity kicks in and dissipates the fluctuations. I will put a lot of pictures up. Next couple pages, so please be patient. The rate at which turbulent kinetic energy dissipates by viscous effects is called the dissipation rate. I promised to define this for you, epsilon. It was in the last chapter. This is the rate that this kinetic energy is breaking down into a smaller scales. It takes a certain amount of time for this to happen. So the rate of the transfer of kinetic energy is known as the dissipation rate. In a statistically stationary turbulent flow, the energy transfer rate at each eddy length scale is the same, which provides a convenient method for the calculation of the dissipation rate. Now, immediately, I would like to make an analogy for you to be able to visualize this. Okay. I'll say analogy. The first analogy I want to make is this. For a statistically stationary, I said something about that, statistically stationary turbulent flow. Statistically the analogy I want to make is, let's say you have a number of buckets . You fill this bucket with some water. This bucket will fill up to some level, and then it's going to pour into the next bucket. And obviously there's gravity pulling down. So the water will pour down to the next bucket. It will come up so that then it flows down over to the next bucket. And again, this bucket eventually fills up, so the water in there pours down to the next bucket. And this keeps going all the way to to the very end, where suppose that the water pours into a lake or pond or something like that. Okay? So you got water coming in. It keeps going down. The analogy is this. Each bucket could be thought of as a given stage of the energy cascade. Think of this as the largest stage. And then these would be I should say I, because each stage has a different length, velocity, and time scales for the eddies to form. So the water is pouring down, and then eventually you reach the dissipation stage where all of the fluctuations by viscosity are dissipated. If all of these buckets are filled near the top, the rate of passing water down to the next stage is the same. It's the same rate. I mean, it's the same rate. Call this rate 1. It's the same as rate 2 is the same as rate I, all the way. So all the rates are the same. Because the buckets are all filled near the top, all these rates of transferring water down is the same. So in other words, the mass rate, the mass flow rate is analogous to energy transfer rate. Which I defined for you a bit earlier, right? I define it with this symbol. Because all the buckets are filled near the top. But I could have a case, that's the other case, that is statistically not stationary. Non-stationary turbulent flow. In this case, the levels of water in each bucket may be different. For example, I may be pouring the same rate of water on the first bucket, but it's not filled near the top. No water is flowing. However, maybe from some moments ago, the second bucket was filled over to the top, and there's water pouring out to the next bucket. Maybe this one hasn't filled up yet, it's partially filled. Maybe even this one isn't filled either. So you see, I can no longer claim that the same mass flow rate of water is occurring between different stages. This is like statistically non-stationary flow, where there is some activity for the eddies, but the rates of transfer of energy, turbulent kinetic energy, are not the same. So let's say rate 1, rate I, these rates are not necessarily the same, could be different. And mass flow rate, and here again, mass flow rate analogous to energy transfer rate. Still, but it's going to be different for each stage. Still analogous, but the rates are different. I hope that helps to convey the message here. So it's only for a statistically stationary flow that all these rates are the same, and the turbulence kinetic energy is breaking down different levels all the way until it dissipates. Go ahead.
Why is the mass flow rate analogous to the energy transfer rate?
It's the analogy. It's in real physics, mass and energy are different things, right? I mean, unless you're talking about relativity, right? But it was just an analogy as an example. If you think of mass as energy, think of it in that way. It's the transfer of energy that's what we're talking about. Now we're talking about energy, right? The physics is about the energy, but the analogy is the buckets of water and passing that energy down. So don't be confused. I'm glad you're asking the question. At the beginning of the process, the eddies have energies in the order of U naught squared. Remember, in physics, kinetic energy is half mv squared, right? So kinetic energy scales with the square of velocity. That's why I make that claim. Of course, the 1/2 is missing here, or the m is not here, because I'm talking about energy per unit mass. Don't worry about the 1/2. It scales with the square of velocity. We are scaling, we are not doing exact calculations. And time scale is also in the order of size of that eddy divided by its velocity. So we know how long that eddy is going to last, tau naught. So the rate of transfer of energy must be in the order of energy of that large eddy by how long it lasts. Remember, this big eddy, after it has lived over tau naught seconds, it will disappear. It breaks into the next. So if you divide the energy of that eddy by the time it lasts, it must mean the rate of transferring that energy to the next stage, which is this stage. Right? So it's not too difficult to scale this process with some basic arithmetic. An interesting result is that this rate is not dependent on viscosity. See, there's no viscosity here in this calculation. No viscosity. That's very profound. And that demonstrates the fact that I said viscosity is not important at large scale. It's all dominated by inertia. But only the Reynolds number must be really large for you to make this claim. Okay? Now is the time to introduce the Kolmogorov hypotheses that help you formulate this problem. Maybe I haven't the 5 minutes, so I'll just underline a few sentences and we look at the more details next time. Kolmogorov hypothesis of local isotropy states that at sufficiently large Reynolds number, the small scale turbulent motions, that means length scales that are much less than the big eddies, are statistically isotropic. Again, isotropic said something about the direction of the coordinate system. It means that the fluctuations don't care about the coordinate system. For example, u squared, v squared, and w squared fluctuations, those variances or normal components of Reynolds stress, are all the same, no matter the orientation of the coordinate system. In other words, at the isotropic scale, the direction in formation of large-scale eddies is lost as the energy passes down the cascade. So initially, it is anisotropic, right? When I look at the eddies at the big scale. But when it breaks down to a small scale, the information about directionality is lost. It doesn't matter. It becomes isotropic. And that was a genius of Kolmogorov. You know what I mean? You can't prove this, sit down and mathematically prove this, but you could have physical intuition and think about this at large scale. It doesn't matter because the flow would tend to behave isotropically. So I think that's the genius in his hypothesis. Like a divine inspiration, if you want. So it is useful to introduce length scale Li, which is usually a fraction of a knot for which this isotropy behavior appears, right? So it's a big scale, it's not isotropic. At some scale, the fluctuations become isotropic. We know that scale as LEI. Okay. I will put lots of pictures for you, so don't worry, pictures are coming. Right now, so we use the picture for it. Remember the example of flow over a building. So now we're trying to explain, put a picture on Kolmogorov hypothesis of local isotropy. We talked about the example of flow over a building. So flow is coming in. We said, yeah, there are instabilities starting from the edge, and then the very large eddy forms. Remember, if the length scale of the flow is big L, that's say this length scale of the building, that eddy 2 is by and large the same length. At this scale, a flow is anisotropic. Let's say if X, Y, and Z were in this way, fluctuations would be different in the X and Y and Z directions. I mean, this eddy would always roll over, tumble like this way, sort of clockwise. It's impossible to have this counterclockwise, or it's impossible for it to be circulating horizontally, right? If this was a 2D flow, that eddy must do this. But when they break down, so if this eddy goes past, eventually it starts breaking down. At some point, it may be reaching that scale, EI. If it reaches that specific scale, EI, at that point, it becomes isotropic. Which means that now it doesn't matter if I rotate my coordinate system Whichever way I rotate my coordinate system, I'm going to measure the same components of Reynolds stress. Like u squared, v squared, w squared will be the same. Of course, this will continue until these eddies are breaking down so small that they dissipate by viscosity. After you watch this happen long enough, it will dissipate eventually. But at some point, the isotropic condition kicks in. So the information about the directionality of the fluctuations is lost. Hopefully, these couple of schematics can help you understand and grasp the concept of the physics of the problem. Now I am at the end of the lecture time. Yeah, so any questions? Okay, that's great. And we'll see you next time. Continue to finish this exciting chapter. And the online viewers, see you next time too.